Hello, I'm going to talk about gold in oil and its role in the formation of gold deposits, and in particular in the formation of epithermal gold deposits. This work is a lightning dash through Lars Kreed's PhD work. Lars has gone home to Germany since he finished his PhD, and this work never got all that much of an outing, so I'm delighted to be able to present it here. I'd also particularly like to acknowledge Frank Reith's contribution to this work. Frank Reith passed away recently, and far too soon, and it's not just his contribution to this work that I'd like to acknowledge, but his insights and enthusiasm to a whole range of projects. With respect to the motivation for this particular project, the association between gold and hydrocarbons has been noted in a whole range of different mineralizing environments. So we've got things like the Carlin Trend in the Nevada and USA. We've got carbon-rich layers in the Victorian gold deposits in Australia. We've got heaps of oil, the gold, mercury, McLaughlin epithermal deposit in California, and then you've got the Carlin-style deposits in China. These observations are backed up by experimental evidence. There's a few studies that have shown that the concentration of gold, or the solubility of gold in hydrocarbon fluids, can be up to the tens or maybe even the hundreds of parts per million. However, what remains unclear is the role played by the hydrocarbon fluid in the ore forming environments. Does it actually transport the gold, or does it just help to immobilize it once the gold has got to the site of mineralization? And this is something that we wanted to investigate with Lars's PhD. So, going to give a quick summary of 3 different approaches that we used. So we did some brine hydrocarbon gold partitioning experiments, so looking at the solubility of gold, not only partitioning between an aqueous fluid and a hydrocarbon fluid, but comparing those results for different hydrocarbons which would be expected to have a high and low affinity for gold. We also used synchrotron research, so we studied gold speciation in hydrocarbon fluids at the ESRF in France, and we took some samples from the McLaughlin epithermal deposit to the Australian synchrotron to look at the textural and composition relationships in the context of the geochemical mapping. Okay, so we'll start with the experiments. We did these experiments at the Curtin Experimental Geochemistry Laboratory at Curtin University using a core test flow-through apparatus. This is a really cool piece of kit, because one of the things that you can do with it is we can sample the top and the bottom of a vessel that's holding immiscible liquids, and analyze those liquids for AU. So we can get the coexisting liquids, and because we're sampling basically in situ, we don't, in theory, have too much of we minimize issues with quenching. We can apply pressure to the flexible titanium cell through a water jacket, and we can get things hot because the whole thing sits in a furnace. Holds 1 to 2 orders of magnitude more gold than the aqueous fluid, so that's all good. Moving on to the synchrotron experiments. So I didn't go, Lars went to the ESRF in France, to the FAME beamline, to use Dennis Testimali's fabulous high pressure temperature cell. What they did was equilibrate solutions of gold chloride with the hydrocarbon liquids, with dodecane and dodecane thiol, and then loaded them into the cell and collected spectra at a whole range of temperatures up to 250 degrees C and a whole range of pressures up to 600 bars. And then we used the results to try and work out what the gold-bearing species are. So these are some of the synchrotron results. These results are ones that you use in a relatively qualitative way. So what you do is you compare the spectra of your unknowns, which are these solid red lines on either side. On the left side, we've got the dodecane thiol. On the right-hand side, we've got the dodecane. And then we compare those spectra of the unknown species with those of known species. So we've got a gold thiol standard here, we've got gold foil, and we've got gold 3 chloride. And you can see that we've got good similarities between those standards and the spectra, showing that gold is probably in solution as a thiol complex with the dodecane thiol up to about 130 degrees C, where it starts to get interesting, and I'll say something about that in a tick. Whereas the dodecane looks very much like the gold chloride spectra right up to 130 degrees C. And interestingly, at 130 degrees C, what we see is a shift towards a spectra that looks very much like that of gold foil, which we interpreted to suggest that we're probably looking at gold nanoparticles at those temperatures. So that's quite intriguing. Okay, moving quickly on to the natural samples. We were lucky enough to acquire a whole bunch of samples from the McLaughlin Gold Mercury mine in California. This is a epithermal deposit where gold is often associated with a whole range of different liquid and solid types of carbonaceous material. And then you've also got all kinds of different silica infills. So you've got these very delicate laminations and lots of information on the cross-cutting solutions, cross-cutting relationships. So we thought that with a combination of petrography, fluid inclusion work, and synchrotron element mapping, we would be able to start to deconvolute the relationships between the gold, the hydrocarbons, the silicification, and where the gold was transported by those hydrocarbons. So there was a whole bunch of results which I don't really have time to show here, but this is a key result from synchrotron mapping at the Australian synchrotron. So this is the sample we looked at in panel A, and pretty much the same thing in panel B. Panel C, you can see what Lars did was map the different layers and map the textural relationship and cross-cutting relationships between those layers, and use those to put those together with the element mapping, which is shown in panel D, where you've got gold in red, arsenic in green. You can see that gold and arsenic aren't always co-located, which is interesting in itself, and little bits of silver in blue. It's a bit complex and we don't really have time to go through it in detail, but if you put together all these relationships, we got pretty good support for the idea that the hydrocarbon fluids were present at the same time as the aqueous fluids during formation of the deposit and during mineralization, and that the carbonaceous material is an important reservoir for gold at the deposit. Given that it holds gold and that it was around when the aqueous fluids were moving, it's logical to assume that migrating hydrocarbon fluids carried gold, but we still don't know really about the length scales or the proportion of gold that was carried in this way. But that still brings us on to the conclusions, where we can see that the two-phase experiments show that gold partitions into organic liquids, particularly when they've got a sulfur-bearing ligand. The synchrotron experiments confirm the complexation of gold with sulfur at less than 130 degrees C, but indicate that nanoparticles may have become increasingly important above that temperature. And then if we start to look at the natural samples, then we see that the hydrocarbon samples and aqueous fluids were present at the same time, and that the carbonaceous material is an important reservoir and potential transport agent for gold. However, further work is necessary to constrain the length scales of gold transport. And that leaves me a few seconds just to show you the acknowledgements.